Welcome everyone to the Research Connection Speaker Series. My name is G and I am calling from the Boston Technology Center in Boston. And today we have a presentation by Mohit Gupta, PhD candidate in Civil and Environmental Engineering at Arizona State University. The presentation today will explore the process of digitizing legacy engineering drawing, focusing on converting them into queryable knowledge graphs. And I want to thank Fope for introducing us to the speaker, and I will hand it off to you to introduce Mohit's background.
Thanks, G. Hello, everyone. Thanks for joining us today. I'm happy to introduce Mohit, who's our presenter today. He's a PhD candidate in Civil and Environmental Engineering at Arizona State University, where his research focuses on applying artificial intelligence and machine learning to real-world challenges in the AEC industry. His work includes the digitization of engineering drawings, 3D reconstruction of construction sites using 360-degree imagery, and remote inspection of hydroelectric turbines. He has authored over 10 research papers in peer-reviewed conferences and journals. And before pursuing his PhD, Mohit got a bachelor's degree in civil engineering and master's in mechanical engineering. He also brings 5 years of professional experience in the AC industry, having served as a senior engineer and as a beam engineer. Today, he'll be presenting one of his PhD projects, transforming static piping and instrumentation diagrams, PIDs, into queryable knowledge graphs using artificial intelligence. Thank you for joining us today, Mohit. Pass it on to you.
Thank you, Fope. Thank you, G, for organizing this. Super happy to be here. And there is a small change. Instead of just presenting one project, I am kind of presenting 4 different projects in the area of applied AI, and all of them centered towards AEC industry. So first project that I would present is regarding the digitization of P&IDs, for which I think you all would have received the abstract for the presentation. Second is, I think, very common in at least your company, which is converting structural CAD, 2D structural CADs into Revit, which is very common for BIM engineers or BIM-based companies. Then third project would be how I was using Gen AI, stable diffusion, to create synthetic data, which would use for training vision models for different use case. And then last, how 3D reconstruction based off structure from motion compares with neural network-based 3D reconstruction methods like neural radiance fields. So let's start with the first project, which is digitization of P&IDs. P&ID stands for Piping and Instrumentation Diagram, which is a type of engineering drawing containing details about different mechanical equipments or different sensors like temperature sensors or pressure sensors. These drawings also have details about how they are connected with one another in form of lines, which basically depicts different kind of piping systems. They can be electrical piping or normal piping, which carries different fluid. So those fluids can be your aviation turbine fuel or any gases. And these types of drawings are commonly found in nuclear plants or chemical industries, cement plants. So this project was done in collaboration with Ascent Constructions, where they wanted to use the P&IDs in order to calculate the quantities of different components which are shown on the drawings. Now we can imagine that this is kind of a straightforward task, which can be performed directly by the CAD tools. If we have their CAD drawings, we can directly use built-in functionalities and get the list of various materials that are being shown in the drawings. But the challenge is that these drawings are not always shared in the CAD format. Many times they're shared in PDF format or in a zip folder containing all the images where these drawings are converted into images. So what happens is that when they are shared in such formats and not in CAD formats, we cannot directly use CAD in order to do this task. Plus, this is a low-level task where we are just calculating the quantities of different materials. However, there are other tasks which companies like Sun Constructions would typically engage in, which is using these drawings to conduct various kind of analysis, maybe regulatory compliance, safety audits, where you want to make sure that the details which are shown on the drawings are following the required regulatory standards. For example, if there is a fire hazard, we want to make sure that there are enough provisions that have been taken. Maybe fire sprinklers have been added or fire extinguishers have been shown. So many of these tasks you cannot directly perform with CAD tools because the information is visual in nature. And this information you cannot directly index with CAD tools. So typically a human in the loop approach is required, where human uses their domain expertise to read the drawings, to perform these tasks, which are kind of spread across multiple documents, multiple drawings. So my goal in this research project was to make this visual information accessible so that the computers would also read the drawings like we do. This would facilitate that the downstream task, which I've highlighted earlier, which engineers perform, can be done more efficiently in a semi-automated or automated manner. So my approach was very simple, that because these drawings are fundamentally composed of three objects. One is symbols, then text, and then the lines, which are showing the connections between different components. So if we can identify all these components and infer how they are connected with one another, we can create a spatial connectivity graph. And this graph, you can convert into open file exchange format like DexP, through which you can convert an image or a PDF directly into a CAD format. So this solves the digitization problem. But still, we have not made the drawing we have not made the visual information accessible. So current version can support the quantity estimation, but current version cannot support the other task, the task regarding compliance checking or reasoning about different connections. So for this, an engineer is still required to read through the drawings or carry out these analysis. But how I approach that, how we can perform this task, is by converting this spatial connectivity graph into a knowledge graph, where the process would come later. So once, suppose we have converted this into a knowledge graph. So knowledge graph is nothing but a more kind of advanced version of a basic graph, which would have more interpretable features. And now with the advancements in NLP, these graphs can be read by an LLM. So LLM would act as an interface between the engineer and the knowledge graph, and you would be able to interact with your knowledge graph and perform these tasks via using the advancements in NLP. Now, for each of these components, there are multiple frameworks, multiple possible options that you can explore. For symbols, there are object detection models like YOLO, Dectron, Tetter, which you can use for identifying such components. For text, Keras OCR or Paddle OCR works really fine. In my experience, I liked Keras OCR more because with Keras OCR, you can also generate synthetic training data automatically, which suits your requirements. So there may be few particular font styles, which is very common in your drawings. There may be few common patterns, like because these are technical drawings, there are the text which is shown in the drawings. These drawings have some kind of patterns which is subject to the industry or to the contractor who is making these drawings. So you can, using Keras OCR, you can generate synthetic data set aware of such patterns so that your OCR detection becomes even more accurate. For lines, common methods are pixel-based traversal and half transform. So you could use any of them. So once we have identified the components, we can generate a graph, maybe in Network X or Neo4j. However, Neo4j is more flexible because then we can hook it up with LangChain, where through LangChain we have the APIs where we can use LLMs like OpenAI's GPT or others. This process looks kind of straightforward, but there were main two challenges which I encountered. One is in the areas of symbol detection, and second was in the area of creating this interface between the engineer and the knowledge graph. So in terms of symbols, the challenge was that there were large variety of symbols. So in total, there were more than 400 different types of symbols that would occur on these P&IDs. And another challenge was that non-standardization of symbols, which is very common across different industries in AEC domain. So what this what problem this creates is that you would require significant amount of human resources in order to annotate your images. Plus, anytime you move from one particular set of drawings to another set of drawings, whenever there is a small domain shift, you would again need to retrain your models. You would again need to annotate a large amount of data, and then you would be able to perform these tasks, which kind of creates an operational overhead, recurring cost. In terms of LLM, the main challenge was that LLM response is sensitive to lexical perturbations. We know that it depends on how we ask the question, and sometimes there is an inherent stochasticity in the response of an LLM. No matter how we ask it, if we ask it again, there is a change in the response. Plus, if we slightly change the question, there are times when we get the right answer. There are times when we may not get the answer that we would want. So in order to tackle the challenge in the area of symbol detection, what I used was class agnostic training, where instead of manually annotating different symbol categories, what we did was we just annotated everything as generic symbol. And then we used few shot classification, in my case, it was one shot classification to identify or to classify different symbols that we have detected. I was also using active learning, where we were using effective data sampling approaches in order to identify the data points which should be labeled, because we had a lot of data to annotate, and we don't want to invest a lot of resources just to annotate the data, because there would be many data points which are not as informative as others. So we can prioritize which data points to annotate. Then in the area of LLMs, I use the approach of contextualization and few shot prompting, which is kind of a standard nowadays, that if we are using LLMs and if we can provide it enough context about what's the underlying database, then you can remove the hallucinations from the LLM response. And in few shot prompting, what you do is that many times, as I said, there are cases. For example, as humans, we can ask questions differently. Different human would ask a question differently. So in order to navigate this landscape of linguistic ambiguity, if we can provide some kind of examples before generating the response out of the LLM, then it provides the grounding to its response, and we get more or less a coherent response every time we ask the question. So when we used the approaches that I mentioned for symbol detection, that is the class agnostic training, active learning, and few shot classification, what we found is that there is significant boost in all the three metrics, where this data set contained 32 types of symbols. I think, yeah, these 32 types of symbols. And we found that all three, recall, precision, and reference score, were kind of improved dramatically. Another advantage of using the approach of class agnostic detection is that once we have trained a model, which is trained, suppose on this data set, which contains these 32 types of symbols, and now we want to use the same model to identify symbols on another data set where we don't have enough overlap between the symbol classes. So even in such cases, because it's a generic symbol detector, it would still be able to find out different types of symbols on the new drawings. And then few shot classification or one shot classification is not very computationally expensive, and also very not difficult for a human labeler to create a data set. So you get robust performance. You can quickly adapt your models to the new styles of drawings. And no doubt, if you are not worrying about labeling each symbol category as a different one, your labeling process is going to be a lot faster. For a small data set containing 32 types of symbols, it was about 2.5x times faster. And as I mentioned, there are hundreds of classes. So this time savings would exponentially increase if we have more varieties in our object categories that we want to find out. So once we have identified all the components, the text, the lines, and the symbols, we can generate a graph. And once we have this graph, now let's look at the process, how I converted this graph into a knowledge graph with text tag parsing. So typically, whenever we have any component, each of the component would come with a text representation of it. So this text would be informative, which an engineer would typically know how to read it. So for example, if suppose this is a tag for any valve, here 25 would represent a unit number, 10 would represent the diameter to which it's connected to, ATF would represent the fluid it's carrying. In this case, it's aviation turbine fuel. 1002 is going to be the line number, and CS is going to be the material, carbon steel. So, and another thing is that we also have arrows on our piping system, which basically shows how fluid is flowing through your MEP system. So what we can do is we can transform this information into a more readable set of features. So these features are then appended to your nodes in the graph. It can be to the node or to the edge if it's the text tag for a line. So once we append these features, these more interpretable or semantic features to your nodes or the edges, we could convert this base graph into a knowledge graph. And now it's easy that now we can design it as a RAG-based system where we have the knowledge graph and someone can then now ask the question and the LLM would query this question, converting into a graph query language in step 2 here, and then searching the answer to the question in the knowledge graph. And contextualization is nothing, but we are providing the information about the underlying graph database. For example, in this case, we have nodes, the symbol nodes and the junction nodes, some of the attributes like their class, their location, an example statistic of their maybe the range or the example, the types of relationships, how things are connected with one another, symbol to symbol or junction to symbol, junction to junction. And in few short prompting, we are providing few examples where what kind of questions could be asked and what kind of graph query syntax that they had to generate in order to get the response. So yeah, so this is the system where we were stabilizing the response from the LLM based on a question from the user. So in my case, I designed 64,000 questions for 4 categories of question types. One is simple counting, where it's just that, yeah, you want to find out how many mechanical gate walls are present in my drawings. This comes under simple counting. Spatial counting, we want to make count which refer a spatial link between components. For example, if you want to find out how many butterfly walls are on the left of, say, pump, then this becomes in the spatial counting. Spatial connections, you could use attributes like you want to make sure, suppose in a pump, we want to give a strainer on its upstream so that the fine particles don't get into the pump or make it or render it useless. So you can ask questions whether my pump has been provided with strainers on the upstream side. So this comes in spatial connections. Value-based is you would give a value as a reference. For example, you can give a value of material, maybe carbon steel. So you want to find out all the piping components which have a material of carbon steel, or you want to find all different walls which have a size of 5-inch. So you can give those values and then get the answer. So we designed this a testing data set for 64,000 questions. And these were my results, where what we found out is typically like normal, that this is the level of context, level 0 to 3, and it's increasing as the level increases. So level 0 is that when we are not providing any context, we are just giving the knowledge graph and asking LLM the question, these 64,000 questions. And in level 3, we are giving both the context and the few short examples. So you can see that, yeah, whenever we didn't give enough context, we were having suboptimal performance. And as the context to the LLM increased, performance got improved drastically. Demo of this is also available for anyone to experiment at this link, where we have this P&ID. There you can ask questions in here, or you can also write your own question, and you can see how the system works. So that was all about the digitization of P&IDs. And now I will discuss about how we were converting structural CAD, 2D structural CAD into 3D Revit models. A bit of context, I joined ASU in 2021, and at that point of time, like the whole world had faced Corona. So many students could not come to US for studies. So under Metaversity initiative, ASU was creating a digital campus through which students could interact with the campus, see how the campus looks like, and then attend the classes virtually. So the architecture department here was trying to make a 3D version of the whole campus. So I myself have worked in the area of BIM and 3D modeling. So I just wanted to work on something through which we could maybe not fully make a 3D model out of 2D CADs, but still give the modelers a starting point. So if they have something like this as a floor plan, we could automatically create something very basic. Okay, that this is the basic plan on which they can start off. So for this, this is our workflow that we had the 2D floor plan, and then we were using semantic segmentation models like mask RCNN to identify these 5 categories of objects: walls, doors, and columns. And once we have trained the model, we can then use it for inferencing. So this was the neural network training and inferencing pipeline. And once we have the model outputs, we would use Revit API to post-process it. Also, we would convert the detections from the image plane to Revit plane so that things look dimensionally they make sense. So this was our 3D model reconstruction aspect of the pipeline. So some of the sample results after training a simple segmentation model for different categories: walls, doors, and columns. In order to use Revit API for walls, we were creating it as a curve type where we would just provide a start and the endpoint. For columns, we would provide the center location. And for the door, we had to provide one host wall ID. I think you guys are more familiar with the Revit API. So yeah, so once we did this, we could convert a structural plan with the detections into a 3D Revit model. This was overall the simple pipeline that we had, but the challenge was there was a class imbalance problem where walls were huge in number as compared to other symbol categories. And another challenge is that walls shape is kind of very different from doors or columns. Doors, columns, they all look rectangular, while squarish, while walls would be very thin elements, which would have a long span. So initially, we trained a single model to identify or to segment all these 5 categories, and we got 76% of mean average precision. But then we tried that why not separate wall and train a model just dedicated to the wall detection. And then because all 4 have different, all 4 categories would have similar area and similar shape, then we can train another model which would just identify those 4 categories, and then we'll combine the predictions of both the models. So this approach gave us around 7% of boost in our performance. So this was good. And yeah, this is all about the second project. And now maybe let's discuss about how I was using Gen AI for image data augmentation. A bit of context again for this project. This project was done in collaboration with Salt River Project, a power company in Southwest. They have hydro dams, they have thermal power plants. So we were collaborating with them on a project for turbine inspection using computer vision. So this is one of the hydro turbines. So when we run hydro turbines, there is some kind of defects that happens, which typically could be corrosion, cavitation, or cracking. And typically, engineers would go into the turbine casing in order to inspect the turbine. And most of these turbines are underground, and there is water overhead. So these turbines are first dewatered in order for engineers to go into it, and this creates and these places are not really safe to go in. I have myself worked in the area of hydro turbines for 5 years before starting PhD. These are built under tunnels and not very safe, not an ideal place for people to be. So the attempt was that we would reduce the exposure of engineers in these places through which they would just capture the data. They don't have to stay in the turbine casing in order to inspect it for many hours. They would just collect the data, maybe LiDAR or the images, and then they would just upload the data, and hopefully there is a system which would be able to then analyze it thoroughly. So in order to do that, we asked for the documentation. They provided us with the images for last 15 years, but the problem was that there were only 62 images which we could find out, which had some kind of defects on them. And most of these images would also have some kind of unwanted artifacts in order to train vision models. For example, we would have engineers' hands, ruler, pen, or different markings that would come into the picture, and also the lighting conditions. So all this makes it very difficult that you cannot train a vision model with just 50 or 60 images. So this was a big challenge in order to develop such a method. So what we wanted is that we wanted to remove all these artifacts which we don't want. So for this, I was using stable diffusion. So given an image, what we would first do is we would segment what we don't want, and then use the stable diffusions in painting, data in painting feature to fill in those missing pixels. We were using control net reference only method in order to do this task. So given this raw image, this is not the raw image, this is the clean image that we have generated from the process that I just explained. So once we have this this clean image, we could generate newer versions of it in order to augment the data. Similarly, for this kind of clean image, we could generate newer versions of this image using stable diffusion. Now, there was a wide spectrum of the quality of images that were generated. And these are some of the high quality images that I'm showing. So in order to classify which is a good image or which is not going to be a good image, meaning which is a realistic image or which is not a realistic image, we collaborated with the engineers. So what we did is that we collected all the real images and all the synthetically generated images into a single folder and gave this folder to 5 engineers and asked them to rate it on their reality score, like 1 to 5, and only kept those images which were scored 4 or 4 above. Because in machine learning, garbage in is equal to garbage out. So we wanted to make sure that we are giving the images which are of high quality, or the images which can kind of fool the real experts. So they are of high quality. So maybe we would use them in order to train the models. So this is how our performance looks like after augmenting it with the synthetic data. Blue line is the one with the basic data augmentation that we use, maybe when we use augmentation. So the original data set, we would just kind of make it blurry or do mosaic augmentation or flipping, rotating. So these are our performance, how it increased when we increase the amount of data in our training set. And the red one is the performance when we combined both the real and the synthetically generated images. So we were seeing at least 5 to 7% of boost whenever we were using synthetic images. Though the project did not kind of end because we still did not have enough validation. So we would be repeating the inferencing on the next year's dewatering schedule. So every year the turbine is dewatered and then they are checked for these structural defects. So the validation would come in next few months of how the system was working. Which now brings me to the last project, which is SFM versus NeRF for 3D reconstruction. So this was a bit of context again. This is an stadium, an ASU stadium, which was getting constructed in 2021. And I think in 2020, NeRF has just came out. So there was a lot of like talk on internet that NeRF could replace SFM. So I was just curious how NeRF would fare in comparison to typical structure for motion, which companies like Doxel or OpenSpace are using. So this was in collaboration with OpenSpace. So this is the data set which OpenSpace provided us with. And to keep my experimentation limited in scope, this is one mechanical room to which we compared the 3D reconstruction. So in here, 3 areas were identified. One is the piping system. Other one is the overhead piping system. Okay, it's moving too fast. And then third is this one box that over which we compared the 3D reconstruction quality. Files were kind of large, so I just posted all the results online here. So first is that we collected the 3D LiDAR scan of the whole room. And for this, we use a tripod mounted scanner, which served as the ground truth, the gold standard. And then these are the reconstructions from NeRF and the SFM of this mechanical room. We had panoramic images, panoramic video. So using those, we were creating these 3D reconstructions. And like I mentioned, I had 3 areas for the comparison. One was those pipes. So the metric for comparison is the cloud-to-cloud distance, where we would overlay the point cloud generated out of NeRF with the original, the ground truth, the LiDAR scan, and then just calculate the average distance between the points from the generated cloud to the actual ground truth. So we found that for NeRF and SFM, both of them, the cloud-to-cloud distance was about 2.5 or 2.8 centimeter, almost similar. For the overhead pipes, the difference was quite significant. For SFM, you can see that the reconstruction was much sharper, while for NeRF, the reconstruction was very hazy. And also because it was kind of dark, there were many of these black points or black pixels, voxels that got reconstructed falsely. So that's one issue that we found with NeRF. And it was very similar for the third object, which was a storage box that was lying there. Again, we can see that the NeRF's reconstruction was, again, very hazy, and the point cloud-to-cloud distance was over 5 centimeters, while for SFM, the reconstruction was very sharp. Both of the NeRF and SFM had same images. And the cloud-to-cloud distance was even less than 1 centimeter. So yeah, it was a very interesting case study, which I also did in collaboration with TU Munich. I think, yeah, so lastly, these are all different papers that I have published in the 4 projects that I've mentioned. There were a couple of more projects that I had worked on, but not in the areas of AEC, so not presented here. And now I'm open to answer any questions if you have. You can also give me suggestions if there are any. If you have also worked on very similar aspects, then yeah, provide suggestions. I know Fope was working on Gaussian splatting. I'm curious to hear how that was. So
Thank you so much. Yeah, do we have any questions from the audience? Comments, thoughts? Yes, please go ahead.
With the 2D CAD or 2D drawing to CAD, how clean was the data? I might have missed that, because generally what I found in the past is that there are usually a lot of discrepancies in the data, a lot of like artifacts that you think it's a wall, but it's not a wall, or a door comes through as a wall. And how well was that managed?
so for us, it was these structural layouts from the, I think, 50 different ASU's buildings. So in terms of layout, many of them were kind of consistent. And like you said, there was this issue that, yeah, there can be a lot of artifacts. But what I have seen is that if the data distribution over which we are training and also testing is similar, then you can navigate those artifacts. For example, here, even though there are many components maybe in this area, which are not just the walls or not just the columns that we were detecting, but still, if we had enough training data points where such areas are already annotated, so neural network kind of able to navigate those complexities, does not get confused with the artifacts. there were still many cases because our accuracy was, our MAP was not upwards of 95%. It was still in the area of, I think, 70s. And the reason was this, exactly the same, because there were a lot of confusion that was happening, because whenever you move from one building to another building, there could be many surprises that you would not have encountered until in your data set. And this was particularly a small data set coming from few buildings.
Right.
So maybe one possible solution could be to expand it, or or use some kind of first data cleaning to remove those artifacts.
The other question is, yeah, so mentioning the symbol sets and the quantity of symbol sets, and then also variations of existing symbols. You mentioned there was, I forgot how many. I know that we've run into that problem in the past, trying to recognize symbols, and especially hand drawn, where the person annotates the symbol slightly different or slightly custom, and we have all the, we have a symbol that might be a butterfly valve, but it's actually something else because, yeah, variation. And so that was a really complex problem that I know that we ran into in the past, of trying to find all these, it's kind of like recognizing handwriting recognition. There's somebody that writes cleanly, and then there's others that you just think it's another language, and and that was a big problem for us to try to decipher. And looking at that, when those symbols came up, I started having bad memories about trying to decipher them. So yeah, so I mean, when did you come up with any plans for how to deal with those unique cases and better handle those variations, and or they're just flagged as unknown?
First, are you talking about the hand writing recognition, or?
The recognition, like symbols, when folks had, these like a lot of custom symbols, and sometimes just not well drawn versions of what you expect as the symbol.
So first is that this was very difficult for us also, because when I started doing this project, we were trying to argue what should be annotated and what should not be, and does this qualify as a symbol or does this not? So main key takeaway for me was that when we were designing the system, the best approach would be just to first train something which can identify all the symbols that you would have on the drawing, and then have a system like a legend sheet through which you can use those legend sheet to filter out what you really care for and what you don't. So you would give, like, as the user or as the engineer or as someone who is expert who is going to be ultimately using such systems, you would give us a list of things that you want to identify. And then we would only keep those symbols which kind of have certain threshold similarity with the list that you have provided. So in using such few short examples, because in engineering drawings, what's the good thing is that your objects don't change appearance drastically. Like, for example, if you are taking the images of humans can like occur in a different manner. They are kind of hidden, say they're going into a room or hidden by a vehicle or something like that. So there are a lot of variations through which like natural objects appear in data sets. But for symbols, you would always have a consistent appearance of them in your drawings. So you can use those legend sheets as a way to filter out what is relevant and what is not. Or it can be an interactive system where user would give or highlight one such system on the drawing itself of what they're interested in, one or two or as many as they want. And then you would run your algorithm on the back end, keep all the detections that qualify, else remove them. So yeah, this was kind of an approach.
That's good. Perfect. Okay. Thank you. By the way, I'm a ASU grad, so
Ah,
shout out to ASU.
That's great.
Hey, Mohit, had a question for you. Sorry I came in late, but for the symbol detection, did you also use mask RCNN or did you use a different model?
It was YOLO that I used.
YOLO. Okay, got it. And
Object detection.
for annotating both data sets, what was your method? What tool did you use?
Tool. Okay. Initially, I started with, I think this was back in 2021, and I was also new to all the computer vision. So then at that point of time, I was starting with label image, label IMG. Then I moved to label studio, and now actually I was using, there is one YouTube content creator called Srini, Srini. So he has created one tool, and I found his tool very useful. It's a small software, few megabytes, and you can then hook it up with SAM-based models or YOLO models to also generate predictions and also to quickly annotate objects. So currently, yeah, my go-to tool is Digital Srini created, and I'm using SAM on the backend to fastly annotate objects, or the trained
Gotcha.
model if that's the case.
Cool, thanks.
Hi, Mohit. Thanks
Hi.
for the presentation. I really enjoyed I really enjoyed all the content you showed. I had a question about the structure for motion and the NeRF comparisons that you did. Do you have any thoughts on which one of those options might lend themselves better for, say, like say if you take that point cloud and you want to segment objects from it and identify objects from the point cloud, or if you want to take those results and feed it into an object detection model, like between NeRFs or structure for motion, or would you just recommend like we stay with the laser scan?
Okay. I think for segmentation, I think first is that NeRF we were using for 3D reconstruction. Until now, I have not seen how it can be used for 3D point cloud segmentation. I believe for point cloud segmentation, we have different neural networks like PointNet or others, segformers.
Yeah.
I think the main use case is the reconstruction, and I don't know how segmentation would work out if we are using NeRF, because NeRF is kind of first creating your 3D space using the images.
Yeah.
Right. And then there are, like, I've seen some methods through which what they do is that they would align the point cloud that has been generated from NeRF with your actual point cloud. And then they would transfer, if you don't have texture, you could transfer those texture properties. And also there are a few papers on which I've seen if you could annotate your images and then generate a point cloud, then also you can transfer those those object classes back to your 3D point cloud.
Oh, that's really interesting. Or like go from like object detection in 2D, and then when you use those same 2D images for
Yes.
the 3D reconstruction, the points that are generated will retain the annotations from the 2D.
Yeah, there is one paper from Yong Dong. I don't think I'm pronouncing the name right. He is from TU Munich, and his PhD was focused on this. So he would annotate objects in the images and create a 3D point cloud and transfer those voxel level annotations back to the real 3D point cloud by aligning them.
Interesting.
Maybe I can look at the paper and send it to you or somehow, yeah.
That'd be very interesting. Thanks.
Charles, did you?
Yeah, sorry, two-part question or two separate questions, being greedy here. One is you mentioned some of this research you did a couple of years ago, 2021, you're using YOLO, MaskR CNN models that have been around for a while. What are some of the latest models that you think are exciting? And, you know, if you were pursuing this research anew today, what would you be interested in digging into from what you've seen? And then the second question is, of the 4 use cases you presented today, what do you think are you most personally excited about in terms of commercial application?
I think SegFormer is one of the latest models which performs really well for segmentation. Then you have SAM. You can also use now YOLO for segmentation. So there are these models which have lower latency, high performance, and performs really well compared to mask RCNN. So yeah, probably I would use those. And in terms of commercial applications and also in terms of doing things differently, I would have the similar answer. This lot of research kind of, I feel in my case, in this particular project, was done away from the industry. So if I could, because industry was we collaborated with some constructions, but they only gave us 3 sheets. What I would have ideally done is that, or could have ideally been done with us, is that we could have collaborated with them over a large data set of real P&IDs. What I end up doing was using a synthetic data set, which had these 500 P&ID sheets. Because this is a very critical problem currently, that there is a lot of legacy documentation which exists today, and they are very difficult to go through. I was reading one report from, I don't completely remember the source, but there is around 9 billion of worth retrofitting or renovation that needs to be done, but it's still not happening. And it's the reason because the documentation for the legacy buildings is very difficult to go through, and that's why the renovation or retrofitting is getting kind of delayed. So I feel there is a lot of market value in this particular area, and also a very crucial need of today's time, because you are going through a documentation of different engineering documents which are spread across multiple modalities. They may be coming from your emails, they may be coming from your drawings, or from your different reports like feasibility reports or detailed project reports that you're creating. So if there is a way through which all of this could be made accessible, and you can create a single source of information, maybe just similar to how Revit is. Like in Revit, you can bring in models from different disciplines and create a single source of truth for your stakeholders. So similarly, if we could combine the information from different sources and make it as a single source of knowledge base, it would work wonders for everyone. So yeah, so I think, yeah, for commercial application, I would go with this. And there are a few startups like Toggle.ai and others which are kind of trying to do similar things, that for your submittals, they are trying to quickly get you to estimate quantities of different things so that you can make your proposals faster.
Yeah, and sorry, one more follow-up question, if that's all right. So my understanding of Toggle and some of the quantity takeoff startups is they are restricted to sort of architectural drawings. The disciplines that they're estimating or that they're automating happen to be the easiest from a manual perspective, like walls, slabs, things like that. And the more tricky things like ducts, pipe, they're not able to deliver value on that. What do you think is happening? I mean, obviously, it's kind of an unfair question because neither of us know the ins and outs. But what would you posit as like the technical hurdles that they're jumping into?
I would say, because I've seen it with SRP, with SUND, I'm not 100% sure of how much data are they being able to get their hands on in order to build such models or provide such services. And many of these tasks would require certain domain expertise in order to truly deliver the value. So maybe from data standpoint, I feel there is still not a large publicly available or large aggregation of data sets, which I believe any company holds, and they are working on annotating it. And this, in my opinion, is the gap. You could do a decent job for these type of drawings, like the architectural drawings, because they are available vastly. Plus, vision models are mostly suitable for them because these the components that you are identifying would have a large ROI in comparison to your image area. So this would translate into a better performance, while for other components, this would be tricky. And because many of the components could be very cylindrical, very, very thin. So, for example, line detection is a very tricky problem until now. Still now, like robust detection of lines, creating proper connected graphs is still a like a very difficult problem for engineering drawings. So I believe, yeah, the nature of data and the amount of data set that you or any company has access to in order to build those models is one of the limiting factor.
All right, I think that is our last question, unless we have any more. Otherwise, I want to thank our speaker, Mohit, for that wonderful presentation. Thank you, everyone, for joining. Thank you, Fope, for making the connection and joining us on your vacation. And for all the awesome questions for our speaker today. Thank you, everyone, and have a great rest of your day.
Pleasure to be here. Thank you.
Okay. Thanks, Mohit. Bye, everyone.
Thank you.
Bye.
Thanks, Mohit.
Bye, Chi.
Bye.